And I'll be presenting you the project EN-PME-Test and its main outcomes. That will be the part one of the presentation, and then I will let my colleague Michael Sattler present the methods in more detail, the methods that we are proposing. So the content of my presentation, so I will give a few words of background. Then I will explain what the project was about, who was involved, and what was its aims. The main outcomes, I will make a focus on 2 work packages of the project, and then Michael will present the methods. So the background. So we are facing a growing use of biomass as a renewable energy. The domestic, as a result, also the domestic sector of using wood combustion is a strong contributor of PM emissions in Europe and in the different countries. And in areas where wood combustion, domestic wood combustion is heavily used, the peaks of ambient air particles are observed. And there are evidence that shows that wood combustion contribute to those peaks. So what are the particularities of wood domestic aerosols emissions? So it's a very fine aerosol, mainly PM2.5 or even smaller than that. There is a high contribution of condensable organics. Robert Burke already spoke about that this morning. And OGCs. And these are particularly, their contribution is particularly important in case of bad combustion conditions. Those organics, so the ones that condensate quickly, and the OGCs, they highly contribute to PM ambient peaks through the formation of primary organic aerosols and secondary organic aerosols. So those compounds are formed once the emissions leaves the chimney. And there are evidence that shows that combining low emissions of solid particulate matter and OGCs, to our knowledge, is a suitable objective to reduce the contribution of residential wood combustion to ambient air pollution. I won't go in detail on the standardization work because it's been already presented, but just to summarize, there has been many years trying to agree on a common European method. I took part to the last 8 years, but I know that there have been many more years and many attempts to reach a common method. So it's a new attempt. So I hope we manage. Okay, so I'm not going to go into detail because this has been already mentioned this morning. So the work on reaching a common European method is taking place in parallel to the work of regulation of the eco-design regulation. So, well, I'm not going to go to mention all those points because they've been already mentioned this morning, but we are in this process of accompanying the regulation process. Regarding measurement methods, well, there are 2 requirements that are necessary to reach for the future. The one is the one that concerns us. The first one is to propose a unique method for the measurement of particulate matter emissions instead of the 3 methods which are used now. So that was the aim of the EN-PME-Test project. And the other one that I won't be talking about today is defining test protocols or firing procedures that are based on real-life operation. And on that topic, there was another project called Be Real, where other people were, or in some cases, same people were involved, and they worked on those tests and those type of protocols. Okay, so what, in terms of the methods that we tried to propose, what were our aims, or what was the requirements that we followed? Low investment costs for the test laboratories. The laboratories which perform the test, the notified bodies, they are not laboratories with, which are used to spend big amount of money on emissions measurements. They are perform different type of tests, but they are not prepared to buy very expensive equipment and very complicated equipment to use, because buying is one thing, but also using an equipment, an expensive equipment, is also very expensive, because you need to have very technical people which have to be trained, and it's quite expensive. Another thing is that we need very low limit of quantification. So the limit of quantification is the values that you are able to quantify, which means that you are able to evaluate the reliability of these values. It's not only the values that you can give, it's the values that you can say, well, you can rely on this value because the uncertainty of this value is such. And we need low limit of quantification because the threshold limit values are going down, and we need to have methods that can be used in front of those values. We need methods that can be well calibrated, or at least compared to other methods that we know of, or the previous methods that we were using. Methods that can be evaluated through reference materials. Well, for particulate matter is not that simple, but at least we need to be able to evaluate them in a process, maybe with reference materials or with intercomparison or things like that. The smallest particles have to be taken into account. We are not saying that we are going to focus on those ones, but they have to be involved, taken into account in the particles that we are measuring. But it's not only the small particles which have an effect on human health. Organics also have an effect, and even the small particles is not. The size is one thing, but the chemistry is another thing. So it's a bit more complicated than just talking about size. Well, as I said before, the volatile organic compounds, or the organics, is something that we want. Is a parameter that we wanted to take into account. The method has to be developed primarily for notified bodies and for the industry, to allow the industry to develop new products or products which are in line with the regulation. And we also wanted, if possible, to use this method for field inspection, but that is kind of complicated. And as we said before, our work only focused on the measurement method. We didn't look at firing procedures. From the beginning of the project, we always say that those methods then can be applied to different type of firing procedure. But it's too complicated to work on both sides at the same time. So that's why we focused on that. So a few words on about the project. So this project was performed under the umbrella of the Aeronet Call. So we call it co-normative research project. Its aim was to establish scientific basis for a test method to determine solid and condensable particulate emissions from residential heating appliances and boilers burning solid fuel. So as we said this morning, the actual standard allows two different methods, which is kind of improved DIN plus method and the dilution tunnel. So it's still not optimal because there is no one unique method. The test method, the aim was to address relevance to health, environment, energy conservation, covering the needs for product development, type test approval, and field inspection. I won't go into detail of the project, but we had a kind of two-step strategy. Quite early in the project, we realized that it was going to be complicated to agree on a very innovative method at a European level. We were 10 countries, 17 partners. So we decided to agree to find the best compromise on a short-term method and to continue working on other approaches for the future. So today we'll be mainly focusing on this short-term approach that we define in the project, but there will be a few words said on the long term also. Okay, so the project, it was a consortium of 17 partners from 10 countries. It involved different institutes, research institutes, universities, notified bodies, many of them involved in the TC295WJ5, and for most of them closely connected to the authorities and the industrials. We always try to get the feedback from the different stakeholders. The funding, it was either self-funding from the project partners, and also some countries were funded by the National Environmental Agency. And there you have the logos of the different partners who took part of the project. So these are the different work packages of the project. So I'm only going to focus on the results or the outcomes of work package 2 and 3, which are the most technical work packages. So the work package 2, its aim was to agree on different candidate methods and to detail them or to describe them and to identify what was the gap, where was the gaps in knowledge, and what was research to be performed to improve the methods. And the work package 3 consisted of round-robin tests with the candidate methods. So work package 2, the main outcome was the definition of different methods. One of them was this short-term method. Basically, this method is nothing new or nothing. It's based on existing method, which was the heated filter and the OGC measurements. But the idea was that there were some lacks or some improvement to be made in this method, especially the particulate matter sampling. And it was improved strongly to make it more reliable. For example, one of the main parameters that influence the repeatability or the reliability of the method is the temperature of sampling. And in the DIN plus method, for example, the temperature of sampling was 70 degrees. But first, it was not mentioned 17 degrees in the flue gas, or only 17 degrees as a setup temperature. We didn't know. Anyway, we decided to use the highest temperature possible in order to sample only the solid fraction on the one hand, and use FID, which is an analysis that many notified bodies are equipped with, that many industrials know already. And it allows the measurement of OGC, and OGC is, first, it's a pollutant as itself. It's a pollutant that is measured, for example, from industrial sources. It's a good indicator of the combustion, of the quality of the combustion, because when the combustion is not very good, the OGC level increase, and it's also a good indicator of the condensable fraction. And OGC are also precursors of the SOAs. SOAs are the new pollutant that many research institutes are starting working on, and for wood combustion is a very important parameter. So this, for all those reasons, OGCs is a very important parameter. You can find appliances with solid PM, not too high or kind of average, but with high OGC levels, and OGCs are very important to deal with. And since the temperature is very important, and depending on the temperature you use, you will sample different species. We decided to use the same temperature for solid fraction and OGC, so 190 degrees for both parameters. And the temperature has to be maintained in order to be able to compare one appliance from one cycle to another, different appliances between each other, you have to sample at constant temperature. That's a key parameter. So we propose the method that allows to maintain the flue gas temperature at the filtration area at 180 degrees. And choosing 180 degrees is a way of avoiding cooling down the flue gas. So this will be explained in more details by Michael. But okay, so what are the boundary conditions of our method? So we use the threshold limit values that were already known in 2011-12. So these are the limit values that we are intending to be able to reach or to be in the range of those values. And our measuring range is much wider because we know that for product development and for other type of application, we need a method that is able to measure a wider range. I talk about the limit of quantification. So these are the limit of quantification that were determined during the project using standards that are used for by INERIS, for example, for industrial emission sources. So for OGCs, we assume to have a limit of quantification of 10 carbon equivalent milligram per cubic meter. And for particulate matter, by using a weighing scale with a low resolution, we can reach 3 milligram per cubic meter. And the operation range, in order to be able to apply this method to a wide range of appliances, from wood log stove to pellet boilers, we needed a flue gas, need the method to be able to be used in a wide range of flue gas temperature. So the aim was from 40 to 400 degrees. Of course, the method hasn't been tested on all those temperatures, but there has been some tests done to show that we managed to maintain our temperature. Work package 3. So the aim of work package 3 was to perform round robin or intercomparison of methods. And intercomparison is a way of determining the uncertainty of a method. So it's a very important step when in a standardization process. So we performed 2 intercomparisons of methods. The first one took place in INERIS in France in February 2014. It involved 13 laboratories from 8 countries. So here, this is the place where the intercomparison took place. So it's a testing bed for emission measurement. So it's used by INERIS to perform intercomparison of the laboratories in France which perform emission measurement from industrial emissions. It's mandatory in France for the laboratories to take part of those intercomparisons. So this bench is equipped with 3 different boilers, and one of them is a pellet boiler. And it's a loop with 12 sampling ports, which have shown to be homogeneous for particulate matter below 2.5. And we've used this bench to perform 3 days of intercomparison using a different method, and one of them was this short-term method, this method for the heated filter. The second intercomparison took place in Czech Republic in October 2014, and it involved 9 laboratories from 8 countries. They designed a bench for the purpose of the project. And during this intercomparison, they focus more on the influence of the velocity of the sampling on the reliability of the method. What are the results obtained from this intercomparison? So for the particulate matter collected on the heated filter, the expanded uncertainty, we got 34% for the particulate matter. So our range was from 6 to 42 milligram, so with the pellet boiler. And with the wood log stove, we got 35% of expanding uncertainty in a range that goes a bit higher. And the best uncertainty was obtained when the velocity in the probe was between 7 and 9 meters per second. So it's one of the reasons why we decided to go for this higher velocity. I don't know if you are very, you know well about uncertainties, if those values may appear high or low to you, but I just want to mention the fact that it's the first ever determination of uncertainties on this type of measurement using a real source performed by simultaneous measurements. Because especially for wood combustion, as it was mentioned this morning, the source varies very much. So if you use the same source and you make it travel from one lab to another, even though you define very well the procedure, there is always the variation of the source that will influence your uncertainty. Here, everyone was measuring at the same time on the same matrix. So we evaluated the uncertainty of the measurement method. That's it. At least we know what is the uncertainty of this method. And it's the first time it was used because before that we performed the validation of our bench at INERIS for the project. So the bench was designed for gas, and we saw that since it's pellet boiler, maybe the matrix is very fine and it's, we get homogeneous flue gas, and we found that it's homogeneous, and it's the first time it was performed. Regarding OGC, we found 30% expanded uncertainty in the range. Oops, sorry. In the range, it's quite a wide range between 16 and 144 milligram. So this uncertainty is quite higher compared to the uncertainty that can be obtained from laboratories that perform emission measurement for stationary sources, because in the last intercomparison performed at INERIS, in a range which is a bit much lower, we found between 12.5 and 25% of uncertainty. But OGC is a parameter that has been regulated for many years for stationary sources, so those laboratories are very much used to perform OGC measurements. And OGC is a bit sensitive sometimes to high concentration. It can get quite dirty, and at high concentration sometimes, well, might not help. So the conclusion of this first part. So concerning residential wood combustion, the stakeholders recognized that there was a need for reliable, unique European method, and the project, the aim of the project was to establish the scientific basis to agree on a common method, and it gathered a wide range of institutes in Europe. We tested several offline and online methods, and we ended up to the proposition of combining the PM collected on a heated filter and OGC measurement using FID. We performed 2 intercomparison of methods, and the expanded uncertainty of the method was determined. For more information, so you're going to have a second presentation on the description of the method. And there is also a position paper that we published at the end of the year 2015, where you have the main results of the project and the description of the method. So I'll let my colleague Michael Sattler give you more details.
My name is Michael Sattler, coming from Switzerland. So I'm a little bit outside of, although we adopt all the regulations from Europe, from the Ökozentrum. It's a center of appropriate technology and social ecology. And I'm sort of the person coming after Christian Gegau, who was already mentioned before this morning. So he's very well known in this area. And I will not reach at least his tallness, but I try to catch up with with what he left thematically. I will talk about the technical details of the method we developed in this project that Isaline just presented. And I'll give some input on the basic layout. We have three main things that are actually different from what you probably know before in heated filter measurements. And it's the probe itself. We did a special heating system on the probe itself. It has also, it's much longer than everything else we saw before. We have the nozzle orientation, so it's not this isokinetic sampling anymore. It's a 90-degree sampling, and we have the deposits in the probe that before were normally rinsed. Now we try to do it with a blowing air, well, just air blowing through it and collecting the deposits. And then I'll give also a short view on what we should improve on this method, because it's, of course, it's never finished, but also we as the project team see that there are some improvements to be made, and a few words to the long-term approach we also developed in that project. So here we see the layout of this short-term method. You see the OGC sampling train, and you see the PME sampling train. And these are actually the two filters. So this is the pre-filter for the OGC measurement, which is at exactly the same temperature as the filter for the particles. And the idea is that actually everything that's solid comes into here, gets stuck here, and here you only measure things that are gaseous at 180 degrees. And here it's the other way around. Everything that's gaseous at 180 degrees will pass the filter and will not be measured. So we do not have an overlap in what we measure. And well, in other methods, there is this overlap. If you do not have a pre-filter at exactly the same temperatures as your particle filter, you will have an overlap. It's not very clear how big this is, but still that's just one condition we gave to the method. Then this 180 degrees, Isaline already said some words about it. Our idea was actually to measure these particles as pure as possible. So we tried in a way to separate minerals and soot from the organic components. And that's the reason why we set this temperature as high as possible. In the discussions we had during the project, we wanted to go up to 200, 300, 400 degrees, but then you run into problems with the FID, so there are no devices that measure OGC at that high temperature, and also you run into the problems just with the fitting and all this. So the PTFE has a temperature, oops, that's the wrong button. The PTFE has a temperature of around, I think, 210 before it's melting. So these components must still be, you must be able to use these components. So in this next slide, this was developed during the project. You see, this is sort of the PME we measure on the filter, the mineral salts and the soot, and this is the OGC we measure in the FID. And of course, we are very well aware that there are some interconnections, so it's not an absolutely straight approach, but at least this was our intention behind all this. The probe itself guarantees the temperature of 180 degrees, not only, let's say, on the outside, but also on the inner wall of the probe. So we do not want any part of the probe that is not at 180 degrees, because we will end up with some problems. If you're colder than this design temperature, you will have condensation on the wall, and if you're higher than the design temperature, you may end up in evaporating something that you already collected on the filter. So there are different reasons for keeping exactly this temperature, and we developed a system to do that. The nozzle orientation is actually something that is just for repeatability. We saw problems in isokinetic measurement at low flue gas velocities, and we saw the possibility that with isokinetic sampling you can have quite big particles that, let's say, by chance get into the sampling train or not. And if we put a 90-degree orientation of the nozzle, we have some sort of a cutoff. I wrote here, I think this sentence setting is more in line with ambient particle measurements. So we are sort of excluding the very big particles with this system. We cannot tell an exact cutoff. I'll show these slides later on, but at least we have an idea on we are between PM20 and PM50 or something, and exclude the very big ones. That's for repeatability of the measurements. And then the probe deposits, normally they are measured after the test day. You rinse your probe, and then you allocate what you get from the rinsing to these different samples you have. And there are quite a lot of problems with this as well. And we came up with just blowing compressed air through this probe. It's a very easy approach, and we could, in first test at least, show that this is quite close to what you would get by rinsing. So this is the setup we have for heating our probe. At the moment, it's a very long probe. It's a 2-meter long probe. I'll show you the graph why. And we have just a power source here with close to 10 volts, and the current is around 30 amps. So you have a plus pole in the middle and the 2 negative poles on each end of this long probe. And the probe itself acts as a resistor, so you can heat up the probe by electricity. A very easy and simple thing. All you need to do is actually you take quite a small tube. So the cross section of your tube, of the metal part of the tube, must be quite small. Otherwise, you will not be able to heat it. You could also attach these poles directly to the stack and to the filter. That way, you would have a perfectly heated line all the way through. So no connections or anything are needed that are not heated. And one thing to the temperature measurement itself. What we measured is actually the temperature on the outlet of the gas on the outlet of this probe. So we had some thermocouples right in here. And for the regulation of the whole system, to keep it at a constant temperature, we have a thermocouple soldered onto this probe, so to not disturb the flue gas flow. But in this way, you can actually calibrate it once, and because the outside temperature is always the same on your thermocouple that you have on the probe, you are sure that the gas temperature that will meet or come onto the filter will be at the value you calibrated before. This is a graph that shows the reason why we have a 2-meter long probe. We see here the temperature, and well, the time in minutes is not that important, but actually what we see here in blue is the gas temperature, so the flue gas temperature at the inlet of the probe. We had it at 400 degrees in the beginning, then we let it drop down to 40 and go up again to 400, which is, of course, in a normal type testing procedure not very often happening, but at least this was the sort of the boundary conditions we gave our method. And within this variation of flue gas temperature, we could maintain a temperature of 180 degrees plus minus 10. So in the beginning, we were close to 190, and at this point where we have the lowest flue gas temperature, we were close to 170 degrees, but always within these specified boundaries. And that comes afterwards also. Of course, if you know exactly that your temperature range in a type testing situation will not be 400 to 40, you can also adjust the length of the probe. Now, the nozzle orientation, we saw that in low flow situations, as we have it normally in small stoves, it's more or less difficult to, now I think here says it precise, impossible, okay, to sample isokinetically. And so we will never be really isokinetic, that's one thing. We have these randomly re-entrained particles in isokinetic sampling. And a simple approach to actually remove it is this 90-degree approach. So I saw there were some shiftings, okay, it doesn't matter. You have not a nozzle that's pointing towards the flue gas, but just on a 90-degree angle with the flue gas. And this cuts off some particles, as you can see here. This is a graph that says, well, how much of the particles are actually sampled on a filter. And this is the particle diameter. And here you have different situations. The meter per second is always the flue gas velocity. And this is 2 millimeters at the probe diameter or the nozzle diameter. Here, ref is in this case stands for 8 millimeters. It says somewhere here it says this, yeah. So we're actually looking at the orange and the red case. And we see that in our normal operation conditions, we would have a cutoff, which is like at the 50% sample fraction of about PM 20 to PM, as I said before, 50 more or less. So this is the range where we have a cutoff with this very basic system of removing the very big particles to increase repeatability in this method. Then the deposits, as said before, we saw a way of changing this system, and we could show that the deposits were normally between 5 and 30% of the total mass. And we had well, problems with, not problems, but rinsing is actually quite error prone. I hope this is the right word in English, but it's really, if you do rinsing with especially with a 2 meter long probe, you really run into problems in handling and how to do it, and you have the chemicals and all that stuff. And we tried to make it much easier. And also the other problem, this allocation of the rinsing you get at the end of a test day to these single tests you do. So you, at the end you have 5 milligrams and you see these different tests. They have different milligrams in terms of particle on the filter, and you allocate this accordingly to this mass you have on the filter is also problematic, and that's shown in this picture. We have here the total amount of dust collected on a filter, and we have the percentage of this in deposits, and if it would be constant, the percentage, you would have a flat line, and that's just not the case. So we see there is no clear correlation, and therefore we said the allocation itself is a problem, and it would be very good to have a rinsing after each, or not a rinsing in this case, a cleaning after each trial. And that's what we try to do with blowing, and we saw that normally we have not more than 30% of the total mass in the probe, and of this 30%, we get out at least some 70 or 2/3 by blowing. So in total, we collect more than 90% of the mass by filter plus subsequent blowing through this probe. And at the moment, we said, okay, that makes it so much easier that we stay with this uncertainty of 10%. You could also add a fixed value or something. But that's what we do at the moment. What are the things that have to be improved? We know that probe geometry is not perfect. 2 meter is a problem. You could have different shapes. You could have a trumpeter, you could have a coil or whatever. And this has to be developed, of course, and also according to what you're really testing. I mean, if you're testing a sauna stove, you maybe need this 400. If you're testing a condensing pellet boiler, you definitely do not need a method that goes up to 400 degrees. So you could actually shorten your probe. And the standardization of this blowing method for rinsing the probe is not very well defined at the moment, to be honest. We did this in one of these tests in Ostrava, well, during 1 week, I must say, and there were quite a lot of samples, but still, it was like one event during 1 week where we tested this. All I know is that many labs do it to clean actually their probe and say, okay, afterwards it's clean, I can restart sampling. So that also gives a hint that it removes quite a lot of what's deposited in a probe. And then this is probably the next step. We have to go together with somebody who normally develops such instruments, and we have to find a way on how to actually manufacture those. Because at the moment it's a prototype for the laboratories, and there are many things to be improved until it can be sold to the laboratories. Now I come to a very short outlook on what we plan for the long term. This is a slide for those who still believe in particle number concentration as a good indicator for emissions. It just doesn't work, but if everybody is convinced, I'll leave that slide. Otherwise, we come back to this afterwards. What we have in mind at the moment, and that goes back to what Isaline said, the OGC are the precursors for secondary organic aerosols in the atmosphere. And a partner institute of ours in Switzerland, Heinz Burtscher and Alejandro Keller from the University of Applied Science, they develop a method to actually age aerosols very rapidly. So they can take flue gases into a little chamber, they add ultraviolet light, they add ozone, and they wait for about 2 seconds or so, and afterwards they have a result where they actually have formed particles that would otherwise be formed in the atmosphere during days or even weeks. And by this, they can actually sort of foresee what happens with this specific flue gas in the atmosphere. And they are planning to do this, and afterwards not a normal mass measurement, but actually a total carbon measurement. So they're building an analyzer at the moment that analyzes every, I think it's 2 or 3 minutes, the total carbon content of what they collect on a filter after this micro smoke chamber. The flue gas comes in, the particles form, they come together with the particles that are already there, and then you collect everything on the filter and you measure the total carbon content of that filter. And this gives you a very good indicator on the quality of combustion. That's for the long term. And at the moment we see a possibility that maybe both methods could join in the future. So the gravimetric as something that is still needed for special fuels, for example, like straw, where you have quite a lot of minerals but no, or nearly no organic components, and add, well, the gravimetric measurement together with this TC measurements after a micro smoke chamber could maybe be a vision for the future. That was it from my side. To the method, I have not talked about the procedure on how we fire the appliance and all that stuff. That's something totally different. We have just developed a method on how to measure things. And I know a few years ago, sort of learned from Christian. He was the one that brought in the dilution tunnel, and now I'm the one bringing in a different solution, and I'm quite convinced of this one. So please feel free to ask questions.